Hello guys, so welcome to this channel. Here we're going to cover some advanced topics in physics that you could learn in your master's degrees, during your graduate degrees in whatever curriculum, and you could in maybe in your PhD courses, etc. So the first lecture series that I'm going to start is going to be about open quantum systems, right? So what are open quantum systems? And what are the differences between an open quantum system, let's say, and a closed quantum system? So, in our basic courses of quantum mechanics, let's say in our bachelor's or in our master's, we learn about all those uh, models, all those toy models, all those little examples of the quantum harmonic oscillator, the particle in a box, an infinite potential well, and all that. So these are the basic, most fundamental, like very simple uh, models that are that we learn in closed quantum mechanics, in isolated quantum mechanics. So in open quantum system, what happens is we don't study systems like that. In uh, in our case, we have the system is interacting with the environment, right? So what happens with the when a quantum system, when a proper quantum system, it interacts with the environment. It's something similar, but I shouldn't. I mean, that's the essence of what the course is going to be about, right? But it's something similar to what you say. You observe a quantum mechanical system, and you see that the that you get only one of the possible results of whatever experiment you perform. Let's say you have the quantum system. You have an electron. You have an electron somewhere in space, and you measure its energy. Okay, so you have an ensemble, you have thousands of copies of the same identical electron, but in all those thousands of copies you make the experiments, the same identical experiments in the same identical apparatus. You see that in each and every case, in each and every one of those experiments, you will see different results. Why is that? That's the essence of quantum mechanics. You have a wave function, and the wave function could collapse into any one of the possible eigenstates of that particular uh, Hermitian operator representing that uh, observable, right? So you know about all that. So what happens in essence when this wave function is collapsing to one of these states? It's actually the quantumness of the particle, the quantumness of the electron, the quantumness of the system is going away. The system is becoming classical, you know. So that's kind of what the environment does, to quantum mechanical systems. It takes the quantumness, it tends to take the quantumness away. It tends to make the system from a quantum system to a classical system. Okay. So today in our first class on open quantum systems, we are going to learn about certain. We're not going to learn about new things, but we're going to uh, review the older concepts that we already learned in our master courses, in our bachelor's degree, possibly. So the fundamental postulates of quantum mechanics. The first postulate asks about where does my system exist? It exists everywhere. I mean, if you go deep enough, the entire universe is quantum mechanical. But that's a different thing. But when I ask this, I ask a mathematical question like, in what space, uh, in what space does my quantum system exist? So all of you know probably the answer to this, the Hilbert space. So do you know why the Hilbert space? It could be any other space. It could be any other vector space, right? Why not? Any vector space with a defined norm, so that you can kind of tell what are the distances between the quantum states, the defined norm and an inner product, so that you can talk about the overlaps between the states and stuff like that. But why Hilbert space? Why not just any other inner product space? We only talk about Hilbert spaces, but not other. Later on, we'll learn about other spaces. But in our, if you've learned quantum mechanics till your masters, you've only heard about Hilbert spaces, and it's there's a chance that you don't know why Hilbert space, why not any other inner product space. So the reason behind that is, let's say you have a harmonic oscillator. So what's the Hamiltonian of a harmonic oscillator? Okay, and what are the eigenstates? We represent that in the Fock basis, and the Fock basis n goes from 0 to 1 till how much? Infinite number. So it's an infinite dimensional basis, right? So what we do is, let's say there's a wave function. It's in a superposition of all the Fock states, right? So we will write it as something like this, equal to 0 till infinity Cn. This is the probability amplitude for the nth eigenstate, and I'm sorry, I'm writing psi once again. So I wrote it as n here, so this will be n here again. So that's how you can represent a certain wave function in the Fock basis. But you see that the summation is infinite. What does that mean? So this summation has to converge somewhere. And it does converge, of course. This is a certain complex number. It has to converge somewhere. And usually what happens is that it's not trivial. It's not obvious. For you add certain functions, you add certain vectors, and you get a certain vector that exists in the same vector space. It could happen that the summation, when you take the summation, the end result, the product, the total sum of all the possible vectors lands in a different space. But that is not allowed in quantum mechanics. If your basis is defined in one space, the summation of all the infinite sum even, it should converge in the same space. So that's the essence of a Hilbert space. So in formal definition for this is that formal definition of a Hilbert space is that it's an inner product space where the Cauchy sequences converge in the same space. So what is a Cauchy sequence? Let's say you have a number, not a just a number. It could be anything. It could be a real number, a complex number, anything. A sequence of numbers. I represent it as psi n. N goes from 0 till whatever. So the Cauchy sequence is, so in that space, let's say you have psi n, so for some n equals m, you will have a psi m. So the Cauchy sequence, convergence of the Cauchy sequence means that in that space, when you take the norm between psi n and psi m, it should be less than an arbitrary number epsilon. So it doesn't matter how small this number epsilon is. You should be able to find an m that satisfies this. So that really, what does it say really? It means that this psi m is coming very, like, infinitely close, infinitesimally close to psi n, right? So that's, and it should happen in the same space. So that's why it's a Hilbert space. So I've rambled a lot about what a Hilbert space is. Let's pick up the pace. Okay. So Hilbert space is a inner product space made up of complex numbers. Let's say we have a d-dimensional space. So it will have vectors with d entries, and all of them will be complex numbers. And it will have certain vectors which will look like this 1 till with d minus 1. Since we started with 0, so we have to put d minus 1 here. And all these entries vi belong to this complex number. Uh, they belong to the set of complex numbers, right? So that's a certain vector in our Hilbert space. Now, any of these vectors, they represent a quantum state. These quantum states can be expressed as a sum of an eigenbasis, as a sum of the basis in which we talk about the Hermitian operator, and it could be anti-Hermitian to whatever an operator. So it has a certain basis, and the any vector in the Hilbert space should be able to be represented as a summation, as a linear combination of those basis states. Okay, so the basis states, let's say I have a kth basis state, it will look something like this: 0. These are all 0, and in the k plus 1th position there will be a 1 and 0, right? So you can express the v maybe. I'm sorry, as summation vk k, right? So this v, an arbitrary vector in our vector space, I'm representing it in the summation of the basis states here, weighted by these amplitudes vk. So that's the mathematical formalism to represent the vectors of Hilbert space in a certain eigenbasis, that is k. Okay, so let's erase the whole thing once again. So we have the concept of an inner product. I should always give the exact definitions of all of these things, because this will be required in a formal course. So you take the vector, you take the vector um, v, and you take a ket of it. That is in the dual space. That you take it in the dual space. So what is this exactly? We wrote the v earlier as this thing: v0, v1 is v d minus 1 for a d-dimensional vector space. So this is a ket. I hope you already know. So the bra version of this would be this. You already know all of this, but I'm just reviewing. So this will be written as v0 star, v1 star, vd minus 1 star, and this also exists in the. This also will have the same dimensionality as the v, because you can only take inner product between two vectors in the same Hilbert space. So is this the ket? The ket will look like v minus 1. So you have a row vector multiplied by a column vector. What does that give me? It gives me a summation from k equal to 0 till d minus 1 of vk star wk, and that's it. And this thing, what is it? What kind of quantity is it? It's complex number. It belongs to the complex number. Okay. And we know that when we take a measurement of a quantum system, there's a certain set of probabilities. But the interesting thing about probabilities, the most obvious, the most fundamental thing about probabilities is that all the probabilities of my of all the possibilities must sum to one, right? So what's the essence of this is quantum mechanics. So what that means is these things, when you represent a certain vector, which I've already done in a certain eigenbasis, this represents the probability amplitude of finding the particle, finding the system in this, in a sense, like you're doing a measurement and you're finding this value upon the measurement. So, I'm sorry, but the probability of the system to collapse to this eigenstate is given by this value, and not exactly this value, but the mod square of this value. So this is a probability amplitude basically. So these things must sum to one. How do I mathematically represent it? It's represented as the vk square k equals to 0 to d minus 1. So this should be equal to, just expand it, vk star vk. You can also write it like this. You can also write it like this. So this is this thing. So this v should be 1. This is also known as the normalization condition. Okay, so we have another thing that we could learn about, that is called the outer product. Okay, let me rub some of it. And what an outer product is, you'll get to learn in the subsequent sections of this series. So an outer product between, say, V and W. Can you notice the difference between the inner product and the outer product? So this is outer product, right? Outer. Can you notice the difference? In this one, it's the bra V multiplied by the ket W. Here it's exactly the opposite. It takes the ket first and then the bra. So this gives me a certain number, a certain complex number. What will this give me? A vector times vector, that not really multiplied like this. It's a different kind of multiplication. So this gives me a matrix actually. So the outer product is defined as, again write it like this, and this one is W star, W is, and the answer looks like a matrix. In this corner it will be this one, in this corner it will be this one, in this corner, and these will all be multiplied term by term, right? So this corner it will be V d minus 1 times W0 star, and this term will be V d minus 1 times W d minus 1 star. This is the definition of the outer product, mathematical definition. What's going to be the use of it? You will learn about these things in the subsequent sections. Now we ask another question. The first postulate we asked about where does our quantum state exist? The second question, the second postulate answers the question of what if I take two systems? Huh? What if I take two systems with two defined by two Hilbert spaces, and I want to study them together? I want to make one system composed of the two systems, and then what kind of space does it make? But how do I define the states, etc., etc. Right? So the second postulate is going to be asking about. So let's write two here. So combinations of two quantum systems. So let's say we have two systems defined in two Hilbert spaces. One is H1 and one is H2. Okay. So let's give a definition to H1 and H2. H1 is defined as the span of certain vectors in a d-dimensional space, Vi, that goes from I equals 0 to d1 minus 1. And let's say we have H2, which is defined as, again, span of vectors Vi or J. Let's call it something else. Let's call it W with J. And J goes from 0 to another dimension, d2 minus 1. So these are the two Hilbert spaces that will compose the bigger system, the system that is combined of the two Hilbert spaces, the mother Hilbert space in a certain way, right? So it will define that. Will the formal definition of this is represented as, let's say, H. H is a tensor product. This symbol is called tensor product between the two subsystems, and this will be the span of the tensor products of this and this. Vi, Wj. Okay, and then I goes from 0 to d1 minus 1, and j goes from 0 to d2 minus 1. I still haven't explained what this is. Okay, so let me explain it. So let's say we have a certain vector psi defined in a certain Hilbert space. It's d1 dimensional. Let's say we have defined this in h1. It's d1 dimensional, right? The psi tensor product of this is taken with another vector in the second Hilbert space, and it's d2 dimensional, and we'll call it phi. So this is certain. Again, write it in the vector form. Psi 0, psi 1, psi d1 minus 1, and then again this symbol that I still haven't explained. 1 phi d2 minus 1. Okay. How do you compute this? What does this give me? So this tensor product, what this does is essentially, when you see something like this, a vector, it could be a matrix, it could be between two matrices, it could be between a matrix and a vector. What this essentially means is that with each of the element of the first, the first of the two things that we're going to take the product of, like psi, it has all these elements from psi 0 till psi d1 minus 1. So the whole vector will be multiplied to each element of this first vector. Okay. So that will give me, so this is d1 minus 1. So it has like d elements in it. This one, d1 elements in it, I'm sorry. and this one has D2 elements in it. So what will be the combined product? So let's say this one times D2 elements, this one times D2 elements. The total, what will be the total number? Exactly, total number will be D1 times D2. So that is the dimension of my Hilbert space. Dimension of my bigger Hilbert space. Times the product H2. D1 times D2. So it will look something like this. Something big. So this one times this one times this one, all the way to, let's say, and then here some of the terms will be, let's write all the terms just for the sake of, so then psi 0 times psi 1 times phi 0, psi 2 times phi 0, and all the way to psi d1 minus 1 times phi 0 until psi d1 minus 1 times phi d2 minus 1. So that is the tensor product that we get by operating this product between the two vectors belonging to the two Hilbert spaces H1 and H2. Okay, that's how you define a certain quantum state between between two spaces, the combination of two spaces. So we have another formal definition. Let's keep this one. I'm sorry. Uh, Now let's say we have two operators belonging to the two Hilbert spaces. An operator A acting on the vectors of Hilbert space A, and operator B acting on the vectors of Hilbert space 2, H2. What did I say? A is acting on the Hilbert space H1 and B is acting on the Hilbert space H2. Okay. So how would you write this? How would you go about writing this? Let's make a little thing like this. So A, let's say it has these elements L1N. This L1. A. Let it be like in N by M thing, right? N rows, M columns. So there's M, and so this is how much? Mn. So this is my matrix A, and the matrix B in a different way, in a similar way, but different dimensions. So it's something like B11, B1Q. It's different. Then BP1, then goes to BPQ. Okay. Now you want to take the tensor product between these two. Again, you will do the same thing. You will take the whole B matrix and multiply each element with it. Each element of the first matrix with it. So what is that? What will that give you? Let's erase these things. You already understood, I hope. So A tensor product of B will be big matrix where each of the elements will be multiplied with each of the other elements. Okay. So the first term will be A11 times B11. Again, this one to this one, this one to this one, till this one to this one. So the element here will be A11 and B1Q. Similarly, the element here will be A M1 times B B1, and the last element here will be, you can guess, it will be AMN BPQ. Okay. The third postulate that we're going to talk about will be asking the question, how does my quantum state evolve with time? Okay. So the evolution of my quantum state. Okay. So we know about this. Evolution of our quantum system. Okay. So psi t, it will be given by a certain unitary operator that will take it from a time t equals 0 to time equals t. And this operator, you will apply it to the psi at the initial point. Okay. So that's a certain, so the essence of what we do. Isolated, system, in a system, a quantum system that is not open. So the evolution is unitary. It's important to remember that the evolution is unitary in closed systems, but it's not always the case when you generalize your system, when you open your system. Okay. From this, you can, if you take the time and derivative of this, you'll get the Schrodinger equation. Minus I by h cross h of psi. Okay. But that's in the case of, this, when the Hamiltonian is time independent. So I've skipped a step here. So when the Hamiltonian is time independent, what does this thing look like? So when the Hamiltonian is time independent, so it does not belong to t. It does not depend on t. It is just a constant of time. So it will be the very known result, psi 0. You take a derivative of this. With this vector time, you apply certain conditions and you'll get this one. But if the h is not time independent, h is time dependent, then you will need to, you can't just do this. This part will break into little slices of time of, let's say, size del t, and this del t will tend to be 0 because this has to be infinitesimal at that case. So in that case, you have this intuition that this will be an integral, but it's not that simple in the sense that it will be time ordered product of minus I, time going from t0 to t. Okay, so there's a certain mistake here. So this is t, right? This will be small t. Okay, h t prime dt prime. So you're taking little changes in ht, little slices of ht for little changes in time dt prime, and you're not just multiplying a certain constant with your variable time. You're taking little slices of time and multiplying the ht in that, and then integrating it because the h is dependent on time, right? And then integrating it from the initial state to the whatever time you're trying to take it to. And what is this then? This only tells me that I can't just multiply these little chunks in whatever order I want. I have to order them so that the progression of time is coherent. Like by coherent, I mean that step by step. So from t, it should go to t plus del t, to t plus 2 del t, to t plus 3 del t, till, let's say, final time t, right? So this ordering, this will be e to the power minus ih this times e to the power minus ih this times e to the power minus ih this. Again, it will be dependent on this thing. Okay, so this should follow a proper order, and this is guaranteed by this operator. This is the time ordering operator. Okay, let's write it here. Dyson time ordering operator. Okay, so we've covered the first three postulates of quantum mechanics. The first one was, let's do a quick summary. The first one was, where do the things happen? Where do the states exist? The Hilbert space. And then the second one was, like, how do I combine two systems into one system? In what space does that exist? Okay. So the second postulate was asking about combination of Hilbert spaces. Third postulate is about the time evolution of our quantum state. And the fourth one will be about measurements, which is an interesting topic, and I'll leave it for later. Okay, this will be a part of the next lecture. So what happens really when we make a measurement on a quantum state? So thanks for tuning in. Thanks for watching this, and have a good day. Bye bye.